Hello and welcome to a fun and exciting lesson on exponential growth. My name is Mr. Bean, and we're going to start off this lesson with a little story. Once upon a time, there was a beautiful princess named Kellerina. Okay, maybe not so beautiful. This princess had been kidnapped by an evil dragon named Dragonbrust. Roar! Okay, yeah, maybe not so evil. Kellerina's father was the king, King Von Sully. King Von Sully offered a very considerable sum of money to anyone in the kingdom that could rescue his daughter from the evil dragon. There was one such brave hero in the kingdom, willing to risk life and limb, Signor Bino, who was... not that Bino. There we go, that's Signor Bino. Signor Bino told the king that he would rescue his not-so-beautiful daughter from the not-so-evil dragon. King Von Sully at first offered $1 million to anyone who could rescue his daughter.
$1 million.
But King Von Sully realized $1 million probably wasn't enough, considering he was the king and all, and he was very wealthy. So instead he offered Signor Bino $1 trillion. That's the same as having 1 million millionaires offer all of their money. Now Signor Bino went to the king and said, "Sire, I don't want to take advantage of your generosity, so being the good person that I am, I have another idea for my payment. If you'll take a chessboard and put 1 penny on the first square, and then double that and put 2 pennies on the second square, and then double it again and put 4 pennies on the third square, and continue that doubling process until you fill up the entire board." After only one line, the king saw that the total amount of money was only a little over $2. He was so impressed with Signor Bino's magnanimous offer, he immediately accepted this agreement. In today's lesson, you'll see how much money Signor Bino will actually receive after the entire chessboard is filled up. This process of doubling is an example of something called exponential growth. And while it may not seem like much at first, you will see how rapidly it increases, and that Signor Bino is not nearly as nice as he appears. So let's get into the bulk of the lesson now, dealing with exponential growth functions. If the variable is not in the exponent, then it is not an exponential function. Here's what that means. You look here at the exponent. Here we have an x up there in the exponent, and that is the variable, and therefore it is an exponential function. It must be in the exponent. Now let me put this another way. Here's how I remember. This is funny. Ready? We have the word exponent, and if you take the x out of the exponent, you get eponent. Exponential function. There's no such thing as exponential function. It's got to be an exponential function. Get it? Okay? Or there's really no such thing as exponential function. Please don't say that in the future. That's embarrassing. All right, so here you have, writing this down in our notes, what we call the initial value, what you're starting off with. And then B here, the base, is a growth or decay factor. Now, for today's lesson, we're focusing just on growth factors. Next lesson, we'll do both growth and decay. This will also set up for when we start doing models, real-world application stuff, and we'll do a lot more of that in the next lesson. A couple conditions with this is that a cannot be 0. If this was a 0, then the whole thing would become 0, and you would just get y equals 0. Okay, that would be kind of dumb, so we're not doing that. A cannot be a 0, the initial value. Also, the condition 2 is the base must be positive, and it cannot be 1. So it's got to be some positive number, and we can't be the number 1. If it was the number 1, then 1 to the x would just equal 1, and it would just be a times 1 all over the place. And so those are the two conditions for exponential functions. So let's identify whether or not these are exponential or not. So for the first one, 2 raised to the x, is this exponential? Yes, it is. And the initial value is, this is tricky, it's a 1, and the base is a 2. See, this is a base 2, and there's a, you don't see it, but there's a 1 times in front of this thing, and so a is a 1. Is number 2 here, is this one exponential? This one is not, and it is not exponential because, we're going to get rid of those lines, because the variable is not in the exponent. Remember, exponential. It's got to be inside exponent. All right, here we have the variable up here in the exponent. That's okay. The base is positive. The number can be negative in front. That's okay. So this one is yes. A is -3. The initial value is -3, and the growth factor is a 2.6. This one here, is it exponential? It is. Now, you might have wanted to say no, it's not, but here's why. The A is a 10. And the base, this is a little tricky. You're not good if you remember this. This is the same thing. I'm going to write it down here. This is the same thing as 1/6 raised to the x power. A negative exponent means you flip it. And so the base is actually 1/6, not just a 6. And then here, this is tricky here too. We're going to get into this in 9.3, 9.4. E is not a variable, and so this is not exponential. In fact, there are no exponents anywhere in this. E represents a number, kind of like pi is a number. E is its own special number. We'll do that later in this unit. Linear versus exponential. Here you have an equation. I want you to write down the equations for these. I wrote those for you, but they look very similar. In the first, you have 2 times x. In the second one, you have 2 raised to the x. So please be careful when you're writing it on your pieces of paper and on your homework practice and all that stuff, that when you have to write 2 raised to the x, that you make it obvious it's 2 raised to the x. Don't write something like this that's kind of hard to tell. Okay, is that 2x, 2 raised to the x? Make it obvious when you're writing these things down. And there's the difference of the graphs as well. Just a straight line versus a curved line that looks exponential. Okay, a few things to write down here about the exponential growth functions. One is that if the b value is greater than 1, fix that here. If b is larger than 1, then it is going to grow away from what we call the asymptote as you move left to right. Okay, well, what in the world's an asymptote? It says here in this paragraph, you want to copy that down, but put this, it's hard to see on here, but I'm going to put a dashed line right on the x-axis. I'll put it just barely above so you can see it, right along the x-axis. This is some imaginary line. You don't see it, but it is going to be a line that the graph is going to approach closer and closer to. Okay, we will talk a lot more about these in the next unit, Unit 10, with Mr. Brust. He'll cover this stuff, but as you move left to right, remember, you're going this way. As you move left to right, the graph is going to be growing away from it if b is greater than 1. And what is the domain? The domain is all real numbers. As you move left to right, all of the x's on this graph, it goes forever. Another way of saying all real numbers, a nice little shortcut, is you put 2 lines like this, and you make an R. This represents all real numbers. Then you don't have to write out the word all real numbers every single time. The range is the y values of this graph, and all the y values are y is greater than 0. Now, what are these dots here for? We'll come back to that later in this lesson. I just want you to have those on here, so just remember we will come back to this. Now we have growth versus decay. So this is our lesson here. We're doing this one today, and our next lesson we'll do decay. So if you're moving left to right, it's going to grow away. Another thing that it could do is if you had a graph that was doing something like this, that would also be growth, because moving left to right, it's going away. Here's decay. Left to right, it's getting closer, or you could have something like this. As you move left to right, it'd be getting closer. But this is our focus today, growth. So for these graphs, which ones are growth functions? This one, as you move left to right, it's getting, actually, I'm not telling you, pause it, and then I'll have the answers appear. All right, I tried to have the answers here pop up for you, and the first one was a decay, growth, and decay. So just remember moving left to right, whether it's growing away from it or decaying closer to the asymptote. Let's create our first graph of these exponential functions, and what we'll do is we're going to plug in some test points. We'll do a little t-chart. I'll plug in the number 0, a 1, and a 2. In fact, I'll even go up to 3, and let's see what we get. If you plug in a 0 here, so just maybe do some side work, maybe in the margins if there's not enough room. So we'll have 1/2 times 2 raised to the 0 power. What's 2 to the 0 power? That's a 1, so we just have 1/2 times 1. So the y value is 1/2. All right, now let's do it with the number 1. Now we have 1/2 times 2 raised to the first power, so that's 1/2 times 2, which equals 1. So when x is 1, the y value is 1. All right, now do this again. We plug in the number 2 into the x value. So plug in a 2 there. We get 1/2 times 4, and half of 4 is a 2. Next one, we have 1/2 times 2 raised to the third power. And let's see here, that means 1/2 times 2 to the third is 8. Not 6, it's 8. And then half of 8 is a 4. All right, so now we have some values that we can plug into this graph. So we go 0, 1/2, and I'm going to switch colors. There we go, a little bit easier to see. 0, 1/2, 1, 1, 2 and 2, 1, 2, 3, and 4. Okay, and now we can see we could keep getting some more points. And we have our asymptote is going to be, this is what the graph looks like. It's going to be very, very close to this thing, and I'm drawing this freehand here, so it's going to be really squiggly. I'm trying not to make it squiggly. And then you start growing up like this, and it grows really fast as you move left to right. That is what this graph looks like. What is the domain? We have all real numbers, all of the x values from left to right forever and ever. And then the ranges are all of the y values that are larger than the asymptote. And the asymptote in this case is the x-axis. See, it's y equals 0 is the x-axis. And so it's above that line. We put y is greater than 0. All right, first one down. So now this box would work. These coordinate points will work for every exponential function that we're trying to plug in, unless things are shifted and translated, which will show how to deal with that. So if you plug in a 0 here, remember, this becomes a 0, b to the 0 is 1, and all you're left with is a. That's going to happen every time. So 0, comma a is a quick coordinate point without having to do a lot of calculations. Same with with the number 1. If we plug in a 1, it's just a times b. So there's another quick and easy coordinate point. Those are two fast, easy coordinate points, along with sketching the asymptote, that can help us sketch these graphs. If we wanted to add another one, you could put this 2 comma ab squared. That might be another one that could be fast. So these would be, we always want to do at least 2 points, preferably 3, to help us sketch this stuff. 3 is best to have if it fits on the graph. Now, before we go on to the next part of this lesson, I've got to make sure I emphasize you are not going to be allowed to use a calculator on this mastery check. And so for the practice and for the rest of the notes, you want to try and do everything you can without needing to refer to a graphing calculator. So that brings us to this. Well, what are these 3 points here? This first one here, that one would be 0, comma, a. So go back in your notes and let's add this in. And then this coordinate point here would be 1, comma, a times b, and then this coordinate point would be 2 comma a times b squared. Those are 3 coordinate points along with the asymptote that can help you sketch it. So now we will graph number 2. I'm going to do this number 2 with you, and then I'll let you try number 3 on your own. So again, we are going to look at the coordinate points 0 comma 1/2. Remember 0 comma a, so that first one, and then 1 comma, if we plug in a 1, it's just going to be 1/2 times 3. Half of 3 is 1.5. You could say 3 halves, leave it as a fraction, or 1.5. I like decimals when I'm putting things on a graph just because it's a little easier. And then if I did a 2, let's do one more so we can get another coordinate point. So 3 squared is 9, and then half of 9 is 4.5. So let's graph them. Switch to my red. 0 and a half. 1 and 1.5. And then 2 and 1, 2, 3, 4 and a half. Okay, so there's our coordinate points. We have our asymptote over here on the left, so it's really close to the x-axis. And then, ooh, much better. Oh, I spoke too fast. I was about to say that was nice and smooth. So it almost looks like a straight line on the left, and then it starts to curve up, and hopefully yours looks better than mine. All right, there's our graph. What is the domain? I'll put arrows on the end here. Goes forever. The domain is all real numbers because it's going off forever. And the range will be all of the y values that are greater than 0. All right, done. Let's try number 3. Before you start it, I'll at least give you this hint. What does a equal and what does b equal? A is equal to -1 and b is the base. B is a 2. So start with that. See if you can graph this one. I'll have the answer appear here in just a second. And there's your answer to number 3. I plugged in a few different points, not just the 3, but then the 3, -8, just to give you an idea where it would be off this graph. This time, because it was negative in front, it's below the x-axis. The domain's all real numbers. And then be careful here. The range was now y is less than 0 because we're underneath the asymptote. Now on to the fun with translations. H and K, this is just like stuff we've been doing all year. We did this with absolute value graphs. We did this with quadratic functions. We keep shifting things, square root graphs, all that stuff. When it's inside the exponent with the x, we're shifting it the opposite way of what you'd expect. So if it says a minus, then we're shifting it right. If it's here on the outside, though, plus k would mean up. So we're shifting it horizontally, left and right, h units, and vertically up and down by k units. Let's do it. So here's our first one. My recommendation is to start off with what were the original points before we shift them. So 0, comma, A would be a 2. Okay, don't worry about this minus 1, minus 4 yet. We're going to completely ignore that stuff for just a minute. Just look at this 2 times 3 raised to the x, and then we'll deal with the other things. So 0, 2. And then we're going to shift that. We'll worry about the shifting in a minute. And then we have a coordinate point of 1, comma 6, because it's a times b, and then we'll shift that. And then we have a coordinate point of 2, comma, let's see, 3 squared. If we do 3 squared times, that's 9, times 2, 18. Woo, that's a big number, 18. And we're going to shift that. All right, so now what is our new coordinate point? Let's write this in red so it stands out. So what we're doing is we're going to add 1 to the x values because we're shifting right. So I'm going to put a little plus 1 up here, plus 1 to all these x values. And then we're going to subtract 4 from the y values because we are going down. So then we go a minus 4 to the y values. So my new coordinate points now are going to be, all the x values are added 1. This one becomes a 2. This one becomes a 3. And my y values, I subtract 4 from them. So now I have 2 minus 4 is negative 2. I subtract 4 from 6, I get a positive 2. Subtract 4 from 18, and you get a 12. Now this coordinate point, this last one, that's going to be way off my graph, but that's okay. These other two can help me. So now let's do this. First thing, maybe in the side of your notes, great place to write this. When you've shifted things, my recommendation is 1, 2, 3, 4. Draw the vertical asymptote, not vertical, excuse me, this horizontal asymptote. Do that first because the asymptote is kind of like your guide to help you know the boundary of your graph. And then we can plug in these points. So we're going to go over 1 and down negative 2. There's one of the points. And where's my next one? 2, 2. So 1, 2, 1, 2. And then if I could go 3, 12, it'd be way off the grid, way up here somewhere. 3, 12. So then I have my asymptote. It's going to be going right along the asymptote, and then it curves up pretty sharp here. It's going to go up really steep, and oh, it's just really hard to make this straight with this electronic pin here. All right, there we go. There is my graph. Domain, easy peasy, all real numbers. That's what it always is for exponential functions. But the range is different. Its y is greater than, because it's above the asymptote. But what's this asymptote? It was shifted down 4, so its y is greater than negative 4. All right, we're done with all of the skills portion of the lesson. Let me go back and talk about real quick our poor princess, Princess Kellerina. What's going on with her, and what's happened with the money that Senor Bino was trying to get. So if you remember our little chessboard that we had, so how much money was there? Well, we need a formula. You don't need to write this part down. Let's just kind of watch this for a second. Here's the formula that would work with this situation. There was 1 penny that we're starting with on the first square, and we're doubling it. Now this x minus 1, don't worry too much about it, but the x represents what square number we're on. If we plug in a 1 here, that would be the first square, because we're not doubling it yet, so we need this to be a 0, so we haven't doubled it. On the second square, we're doubling, so don't worry too much about this. Here's the formula. If we then plug in 64, because there's 64 squares, we'd get how much money is just on the last square. So if we do this, plug in our trusty calculator, we get some crazy thing like this. 9.223 times 10 to the 16th power. How big is that? 92 with a bunch of other numbers behind it. Look how long that is. That's $92 quadrillion. That's how much is right here on the last square alone. Half of that would be here. Senor Bino would have, basically he's bankrupting the entire kingdom. So poor King Von Sully did not really get a good deal out of that. He thought he did. That's how fast exponential growth can make things get larger, that fast. $92 quadrillion on the last square. Awesome. That's a lot of money. All right, that's the end of our lesson. Good to be with you, teach you about exponential growth functions. This is Mr. Bean signing off. Rock that mastery check, and I'll see you in the next lesson.